infrastructures, cars, trains, ships, machines, production lines, cranes, appliances, elevators, kitchens, tech, spaceships, aeroplanes. Almost everything around us is made of steel. Steel is one of the widely used engineering material. In fact, we cannot imagine this modern world without steel. But all steels are not the same. Different steels have different compositions, and each is made for a specific purpose. Some steels are used in structural work. They offer good weldability, are ductile and economical to build heavy and tall structure. Some are made for withstand heavy loads and impacts. Some are designed to carry bearing load. Some are made for a spring function. Some are chosen for aesthetics, for a smooth, shiny finish that resists rust for decades. And some steels are hard enough to cut and shape other steel parts. So as an engineer, especially as a mechanical design engineer, choosing the right type of steel, or more specific, choosing the right steel grade is extremely important. But here comes the challenge. There are around 300 to 500 unique type of steel grades, defined under more than 6-7 international standards. And this results in over 3,500 different steel grade names. Each standard comes from different countries or industry. For example, in USA, for automobile, general mechanical design and manufacturing, they mostly follow the SCC standard. But for construction, structure works and piping, they use ASTM standard, American Society of Testing and Materials. In Europe, they follow ENISO. And in Germany, DIN standard is quite common. Japan uses JIS standard. And in India, we have BIS standard, Bureau of Indian Standards. But in India, there is another problem at the ground level. Most steel grades available in market are not labeled according to Indian standard, according to AISI standard. For example, plain carbon steel usually sold as MS, mild steel, without any specific grade. You will heard that name like MS pipe, MS angle, MS plates. No grade mentioned. And on other hand, stainless steel and tool steel are often available using AISI standard like 316 or 304. And for tool steels like D2, D3, H13 or O1. While the alloy steels in India are usually available in old EN standards like EN19, EN24 and EN31, which are old British EN standard. And here is the surprising part. These EN grades were actually declared obsolete decades ago and has been replaced by ENISO standard. But still, they are extremely popular in India, especially in a small or middle scale industry, just because people's familiar with this name. And the funny part is we rarely use Indian own official standard for the steel grade, BIS steel grade. You will probably only find those mentioned in government documentations. Now, it's also important to understand that all the steel grades are not available everywhere. For example, there are more than 150 types of stainless steel used globally, but only around 60 of them are commonly used in engineering and in industrial applications. And in open market, you will typically find just 5 or 6 grades available. So this is why, as an engineer, we must know that which steel grades are popular and available in market and by what name they are sold. And once we know the steel grade name in one standard, we can find its equivalent in all other standards. This is possible because most of the steel grades are shared and overlapping across all the standards. For example, SC304 is one of the most common stainless steel grade using in the USA and also in India. That's the same steel is also listed in other standards. In Japanese JIS standard, it's called SUS304. In ISO, it's X5 chromium nickel 1810. In DIN, it's 1.4301. These all refers to the same steel with same chemical composition, just have different names under different standards. So if you know even one steel grade name under any standard, you can easily find its equivalent grade in other standards, either through a quick search online or from a standard reference book. So hi there, this is Ayush from Master Mechanical Design and welcome you to the first lesson of engineering material. In this series, we will cover all most commonly used engineering materials, all types of steels, carbon steels, alloy steels, stainless steel and tool steel, along with aluminum alloys, different synthetic polymers and the engineering rubbers. In this video, first we will understand that how the different types of steels are manufactured. Next, we will understand how these steels are further classified based on their application. And then finally, we will explore the popular steel grades used in industry, especially those are commonly available in the market. Now, technically, the stainless steel and tool steels fall under broader category of alloy steel. But in practical application and industrial catalog, they are kept separate. So we will cover stainless steel and tool steel in a separate video. So what is a steel? So steel is an alloy. An alloy simply means a material that not made from a single element, but a combination of elements. One element is present in major quantity called base element, and other elements are mixed in a small quantities to improve the mechanical and chemical properties. In case of steel, iron is the base element, and the elements like carbon, magnesium, chromium, nickel, molybdenum, vanadium, tungsten and many more are added depending on the grade of steel. Among all these, the carbon is the most essential element in steel. It gives steel hardness because the pure iron is too soft to be useful. And now how the steel is made. So the steel making start with iron ore. Iron ore is a natural rock and minerals from which the metallic iron is extracted. Iron ores found in many parts of the world, especially in Australia, Brazil, China and India. And this is one of the most mined material in human history. According to British Geology Service, around 3 billion tons of iron ore were mined in 2019 alone, which was 94% of all metals mined that year. And 98% of iron ore goes into steel making. There are mainly two types of iron ore. Hematite, which contains 60 to 65% iron content, and second is magnetite, which contains around 30 to 45% iron. So hematite is considered better. But these ores are mixed with impurities, waste materials like silica and alumina. So the first step is remove the impurities. So the raw ore is crushed into small pieces and grounded in fine powder to increase the surface area for better separation. And then process like screening, washing, palletization or chemical separation are used to isolate the iron from impurities. And then the clean ore are ready for iron making in a blast furnace. Inside the blast furnace, we charge iron ore, coke for heat and carbon, and limestone to blend with impurities. Then the coke burns in hot air around 2000 centigrade, generating the carbon monoxide, which reduces ore Fe2O3 to metallic Fe, iron. And at the same time, limestones act as a flux and blends with impurities like silica, alumina to form a slag, which removed manually. Then final results is molten iron, known as pig iron. And the pig iron has around 4 to 5% carbon, which is too much and still have some impurities. So the next final step is the steel making, where we refine these pig irons. The goal is to reduce the carbon content and remove the impurities from pig iron. And this is done in a basic oxygen furnace, BOF. Here, the pig iron is poured into the furnace and high purity oxygen is blown at high speed. The oxygen reacts with carbon to form CO and CO2, and the carbon content drops down to 0.2 to 1.5%, depending on the desired steel grade. Other impurities like manganese, silica, sulfur, and phosphorus are also removed during this step. So yes, in a steel making process, we actually do not add the carbon, we actually remove the excessive carbon. And this is why making a low carbon steels take more efforts and more cost than making a high carbon steel. This is why the cast iron, which has over 2% of carbon, is cheaper than the steel. Now, the output from BOF is the carbon steel, which is poured into a ladle to further refinement, where we adjust the carbon level precisely. To increase the carbon, we add carbonizers like graphites or petroleum coke. And to reduce the carbon, we use lime or oxygen lancing. But if we want to make alloy steel, we add other elements. Magnesium for improving the toughness and hardenability. Chromium to improve hardness, wear resistance, and corrosion resistance. Above 12% chromium, the steel becomes stainless steel. Nickel to add toughness and corrosion resistance. Vanadium refine the grain size and improve wear resistance, the key elements for the tool steel. Molybdenum improves the strength and the high temperature, and the tungsten gives the red hardness, important in high-speed cutting tools. And many other elements can be also added depending on the steel grades. And after alloying, the molten steel is cast into ingots or the plates or sheets. Now, the steel is not only the most used and most mined material, it's also one of the most recycled material on the planet. Around 60% of steels is recycled every year. And when we use scrap steel, we don't need to go through the blast furnace and BOF routine because already carbon percentage are low in recycled steel. So we use an electric arc furnace, EAF, instead. In this process, we melt the scrap steel using the electric arcs, and we can still add or remove the carbon and also can add the alloying elements as needed. And this is how we make a steel. The easiest and least expensive steel is the carbon steel. We simply remove the excessive carbon from pig iron in a BOF furnace, basic oxygen furnace. And then comes to alloy steel, where we add the different alloying elements into the carbon steel to further improve its mechanical properties. Now, if the total alloying elements, including carbon, are less than 5%, we call it low alloy steel. It's offer a balanced mix of strength, toughness, and cost. widely used as general purpose machine parts. For examples, EN19 and EN24. And if the total alloying percentage is more than 5%, we consider it as a high alloy steel. Known for its excellent hardness, wear resistance, strength, and corrosion resistance. Perform better in specific conditions like high-speed tooling or high-speed temperature application. But of course, it's more expensive. More alloy means more cost. Most high alloy steels fall under either stainless steel or tool steel categories. For example, SC316, EN31, D2, H13. So we can broadly classify all the steels in four main categories. The carbon steel, alloy steel, mainly low alloy steel, stainless steel, and tool steel. Now, you may argue that I use the steel is already an alloy. Isn't carbon steel is not an alloy? Because it has iron and the carbon. There is two elements, so it's an alloy. So why only some steels are called alloy steels and some are not? Some called stainless steel or the tool steel. Why? So technically, yes, you are right. But in engineering standard, any steels that has intentional alloying elements beyond the carbon and magnesium is considered as alloy steel. But in a practical market terms, we only labeled the alloy steel when they are not stainless steel and the tool steel. Now, before we go in deeper in any type of steel, let me first quickly give you an overview of a steel grade standard. So it will become easier to understand the classification and the naming of steel grades. Or you can skip the chapter, but better you don't skip. And if you have enjoyed this video so far, please give us a like. So at this present time, we have more than 6-7 major steel standards actively using across industries. But that was not always the case. Over the time, many standards has evolved, some has merged, and many has been obsolete. These standards are mostly defined the country-wise or region-wise, and each uses its own nomenclature styles. Some includes only the chemical compositions, but others also includes the mechanical properties, the manufacturing conditions, and the testing procedure. For example, SCC gives a simple numerical identities based on chemical composition. ASTM goes a step further and includes testing methods and mechanical specs, whereas EN ISO standards are even more detailed, offer a specific delivery condition, weldability, and many things. So these standards do not just differ in naming, they also differ in their depth and detailing level. So in this section, let's look at the all major steel standards currently in use, along with the one that's now obsolete but still widely used in India, the old British EN standard. So first is SC, American Iron and Steel Institute, and SAE standard, Society of Automotive Engineers. They are American standards mostly used in North America, India, and globally in automotive and tool steel industry. SC and SAE were separated system until 1995. After that, SC officially withdrew from maintaining the steel grades, and the system is now fully merged in SAE standard. They are popular because their naming is simple, like 1045 for medium carbon steel or D2 for tool steel, and the numbers directly reflects its chemical composition. Then we have ASTM, the American Society of Testing and Materials. Unlike SC, ASTM includes chemical, mechanical, and testing method specification. It's widely used in engineering, construction, and oil and gas industry. For example, A36 as a structural steel, having detailed chemical composition as well as mechanical properties, and also the mechanical testing procedure. And then we have the most precise standard, EN-ISO. EN, European norms, and ISO is a global standard body. And when it's adopted by the Europe, it becomes EN-ISO. Their naming is based on chemical composition, not just a random number. Widely used in Europe, Middle East, and even in India for export. Then we have GIS, Japanese Industrial Standard, used in Japan and across Asia, especially in automotive, electronics, and tool steels. GIS standards are also known consistency and precise classification. Prefix like SUS for stainless steel, SUS 304, prefix like SK for tool steel, and there are many more. And then IS, Indian Standard, Bureau of Indian Standard, BIS, the Indians' own standard system, heavily influenced by old EN grades but modernized to match with global specs. For example, IS 2062 is a mild steel, equivalent to A36. IS 1875, equivalent to C45, used in government tenders and local manufacturing. Then we have DIN, German standard. This is the old German standard, once very popular in automotive and machine design, although now it's merged with EN-ISO standard. And then EN, the European norms. This is the old British standard, which is now absolute but still widely used in India and in local machine shop. This used the simple codes like EN8, EN9, EN19. It doesn't directly show the chemical composition, and the grades are well known and equivalent exist in other systems. It's still very popular due to simplicity and latency use. So this was the all steel standards across the world. And now let's explore the type of steels and their popular grades. So if possible, please take some notes. So let's start with carbon steel. Carbon steel is the most basic, economical, and widely used type of steel. In its very simplest form, it contains two main elements: the iron, the base metal, and the carbon, the main alloying elements. Sometimes it might be a small amount of magnesium or silicon, but not significant alloying elements. The carbon improves its hardness and toughness of steel. Otherwise, the pure steel is soft and lacks strength. But there is a trade-off. As the carbon content increase, the hardness increase, but weldability decrease. So high carbon means high hardness, but poor weldability. Low carbon means low hardness, but good weldability and ductility. So there's even a formula to estimate how weldable a steel is. The formula called carbon equivalent. If Ce is less than 0.4, so weldability is good. But if Ce is more than 0.5, it may need preheating and control. Otherwise, steel can crack or fail to fuse properly during the welding. Now, based on the carbon percentage, the carbon steel are broadly classified in three categories: low carbon steel, medium carbon steel, and high carbon steel. Low carbon steels are also called as plain carbon steel, contain less than 0.25% of carbon. It's a soft, ductile, and highly weldable, and has good formability, but low strength as compared to medium carbon steel. And it's a cost-effective and widely available. Used in welded structure, automobile body panels, the MS pipe, the MS angle, structure tube, because they are easy to weld. Also, we used as a machine base plate and the general structural component in a machine design. And in Indian markets, it's commonly known as MS, the mild steel. Typical grades are 1010, Very low carbon steel used for deep drawing parts and automobile panels. A36 around 0.25% carbon used in general structural framework. SS400 in JIS standard, commonly used in Japanese drawing and for the beam plates and welded structure. And there's one more popular low carbon steel grade in JIS standard, SPHC, used in sheet metal. Now, the medium carbon steel. Carbon content 0.25% to 0.6%, and they offers good strength, moderate weldability, and it's also heat treatable, mainly surface hardening, and commonly used for the shaft, axles, pins, gears, crankshaft, and the forge and bolts. And the popular grades are EN8, C40, widely used for the shaft and axle, EN9, equivalent to C55, used in gears and high stress components, C45, commonly used in forgings, bolts, and the pins, also 1040 or 1045. Then high carbon steel, carbon content 0.6% to 1%, sometime up to 1.2%. High hardness, but that means low ductility, poor weldability, and more brittleness. Excellent wear resistance, but not suitable for shock loading, impact loading. Used in knife blade, cutting tools, springs, hammers, punches, or high strength wires. Popular grades are SC 1060, 1080, 1090, EN42, in Japan SK5. Now, the high carbon steel can be hardened up to 50-60 HRC, no doubt, but they can become very brittle and cannot take a shock loading or impact loading. So they are not suitable for regular cuttings and the punching tools. So for such applications where hardness is required but there is also impact loading, then the tool steels are more suitable. They have the alloy elements to balance the hardness and the toughness. We will cover tool steel in a separate video. Now the cast iron. So cast iron is basically iron with very high carbon, more than 2%. And because of high carbon, it's not ductile, it's brittle, but it's excellent in compression. Now, if you're thinking why it's called cast iron, so it cannot post or roll like a steel. It's poured into a molds in a liquid form. So it's called cast iron. Cast iron is very fluid when it's molten. So it's easily fit in a complex shape. And once it's solidified, it can be machined but not rolled or drawn. There are mainly two types of cast iron. One is grey cast iron used in machine bed, lathe beds and engine blocks. Common grades are FG200, FG260 and the white cast iron used in wear plates. Grade are A48. Cast irons are very common for static loadings and where the damping is needed to reduce the vibration, and where the cost is critical. So the key conclusion is use low carbon steel for easy fabrication. Choose the medium carbon steel when strength matters more than ductility. And go for high carbon steel when wear resistance is the key. But avoid using it where welding or shock loading are involved, and where the strength isn't important as vibration damping and the casting complex shape, then cast iron is your good friend. Basic carbon steel is good, but sometimes we need more strength, more ductility, more corrosion resistance, more wear resistance. That's where alloy steels comes in. We add alloy elements like chromium, nickel, molybdenum, vanadium, magnesium, and many more to improve the properties. Sometimes we name it on the basis of the main alloy elements added, like chromium nickel steel, and sometimes on the basis of its application, like bearing steel, spring steel, or case hardening steel. So first we have a structural alloy steel, low alloy steel. This is the steel we used where parts needed high strength, better ductility, toughness, and wear resistance more than the plain carbon steel, but still the cost effective. But not for extreme environment like corrosion or high temperature, just a strong, reliable, and economical. We use like in shaft, pins, machine spindles, frames, heavy duty moving parts, and the steel grades for moderate strength 4140 or EN19, for high impact load EN24, and there are some other grades. And then bearing steel, a high carbon, high chromium steel built for rolling contact application. It has excellent wear resistance, compressive strength, and fatigue life, but poor weldability and poor ductility. So it doesn't use for shock loading or welding. Used in ball bearings, roller bearings, bearing race, and the precision components. The popular grades are EN31 and other. Then we have spring steel, designed to store the energy and bounce back, perfect for components that deform and return repeatedly, need high elasticity, fatigue resistance, and yield strength, suspension spring, clutch spring, snap ring, measuring tapes, blades, washer, hand tools. The main elements are the carbon 0.5 to 1% strength and the hardness, and silicon for improving the elasticity, chromium, magnesium, vanadium for fatigue, wear, and high temperature. And these are the popular grades in different standards. And then we have automotive alloy steel, used in the parts that faces repeated stress, friction, and temperature, like gears, shafts, and driveline parts. And these are the popular automotive alloy steels. Then we have electrical steel. Electrical steel is also known as silicon steel or laminated steel. This is a special type of steel made for improved magnetic properties, and these are mainly used in electrical devices where effective magnetic flux is needed, like transformer, motor, generator, and inductor. Main alloy elements is silicon, usually 1.5 to 3.5%. Silicon increases electrical resistivity and reduce ED current losses. It's also improve magnetic permeability and reduce the hysteresis losses. There are typically two types. One is gain-oriented electrical steel. Magnetic properties are optimized only in one direction, in rolling direction, mainly used in transformer core, and the popular grades are M3, M4, M5, M6. And second is non-gain oriented electrical steel. Magnetic properties are uniform in all directions, used in rotating machines like motors and generators. And these are the popular grades. For example, M19 is widely used in motors. Electrical steels are made in thin sheets or laminated and can stacked. Then we have weather steel, the rust on purpose, but form a stable outer rust layer that stop deep corrosion. That's why it's called weathering steel, often known as and trade as core 10. The main elements are copper, phosphorus, chromium, and nickel. All helps to form a protective oxide film used in a bridge, railway tracks, and the towers. And these are the popular grades. Then we have nickel alloy steel. 1 to 3.5% of nickel, often with chromium, used when strength and toughness is needed, especially at low temperature. Used in a shaft, crankshaft, aerospace, and heavy gears. Popular grades are EN36, the nickel case hardening, and then chromium molybdenum steel. Contain chromium and molybdenum, provide high strength, wear resistance, and heat resistance, used in spindle, axle, die holder, automobile, and pressurized parts. Popular grades are AC 4130, 4140, 4340. Now, if you are still confusing that which one to be choose, here is a quick summary table for your reference. And I will leave this table in video description, you can download it. So this is it for this video. Next we will explore the stainless steel and the tool steel. So next video should be on your screen or you can check the video description. And thank you so much for watching this video.